So today we're going to start analyzing some three-phase circuits, and we are going to kind of start by looking at things the hard way, and we're going to develop a much easier way to look at these circuits. So let's call this balanced. So we're going to start by looking at a YY system. So I have over here on the left-hand side of the page a Y-connected source with a neutral connection available. I'm going to call this terminal lowercase a, lowercase b, lowercase c, lowercase n. Over here on the right-hand side of the page, I'm going to put a Y-connected load. ZYA ZYB ZYC. Did I remember? Nope, hold on. Stop video. Your screen. Sorry about that. Actually, sorry, I shouldn't have an impedance here. Distracted myself. So here is my Y-connected load, capital A, B, C, and N. And connecting our source to our load, we will have transmission line. So I'm going to have some impedance ZWA representing the transmission line connecting the source to the load for A phase. ZWB transmission line. Here's my C phase transmission line. And then I'm also going to have some impedance representing my neutral conductor. Like so. All right. So let's talk about what it takes to balance this circuit and explicitly what that means. Okay. So this circuit will be considered balanced under following criteria. And let's start on the source side of things. Okay. So we need the magnitude of the phase voltages at the source to be equal. So that means the magnitude of VAN must be equal to the magnitude of VBN, must be equal to the magnitude of VCN, and we'll call this simply VP, our phase voltage magnitude. Second criterion is that the phase separation between the phase voltages is 120 degrees. So the angle theta BN must be equal to the angle theta AN minus 120 degrees, and the angle theta CN must be equal to theta, excuse me, that's not a theta, BN minus 120 degrees, which is the same thing as theta AN minus 240 degrees. So under these two constraints, which we actually talked about in class on Tuesday, our source is considered a balanced three-phase source. So we need all of our voltages to be identical in magnitude, but separated by 120 degrees in phase in order for our system to be balanced. There aren't really many situations to where our source will ever be unbalanced because it requires effectively manufacturing error or us intentionally messing with it in order for that to happen. So largely, this is going to be a given in any system that we look at. Now let's talk about our what makes our transmission line portion balanced. So we need our transmission line impedances must be equal. So this means that the impedance I have labeled as ZWA must be the same as ZWB, must be the same as ZWC, and we'll just call these in a little bit a single impedance ZW. So let's talk about what it would take for these transmission line impedances to be equal. Anybody have any thoughts on that? So I'll get to that in a second, but you're 100% correct. I intentionally did not include the impedance ZN here. So when I'm talking about my transmission line impedances, I'm talking about the things that's connecting the A phase of the source to the A phase of the load and so on and so forth. The neutral conductor, its impedance can be different and the system still be balanced, and we'll talk about that in a moment. But let's get back to my original question. How do I ensure that the impedance of these conductors is the same? Exactly right. They just need to be the same type of cable and the same length. That's all it takes. Now, Colin mentioned that your name is Colin, right? Yeah. That I did not include the impedance ZN here. The neutral conductor does not have to be sized the same as any of our phase conductors. The reason for that will become obvious here in a moment when we look at a balanced system. I don't know how many of you are big enough nerds like me to have a National Electrical Code book on your desk or anything like that, but there are very specific rules for sizing phase conductors based on the amount of current that they're going to be carrying. It also depends on where they're physically located, whether they're in open air, whether they're buried, whether this, that, and the other. So there are very specific rules for sizing those phase conductors, and there's very specific rules for sizing the neutral conductor, but they are a different set of rules. So there's nothing requiring the impedances of these conductors to be the same. And in fact, the neutral conductor is usually significantly physically smaller than our phase conductors. All right. So now let's talk about the load side of things. We need the load impedances must also be equal for this system to be balanced. So that would mean that our impedance ZYA is equal to ZYB would be equal to ZYC. And since they're all equal, we'll just call them all ZY here in a moment. This is the point in our system where we, as designers and all of that kind of stuff, have a choice in things, right? So if we were connecting a three-phase motor or something like that, chances are it's going to represent a balanced three-phase load or something extremely close to a balanced three-phase load. Other things might not be. So the circuit analysis that we are about to do is going to start with an assumption that nothing is balanced, and then we are going to see how things simplifies when we require that our system is balanced, okay? So we are going to start our analysis by looking at the line currents of our system. So as I mentioned in class on Tuesday, the line currents are simply the currents that are flowing through the transmission line. Excuse me, this should be BB. Because I'm going to wind up writing a Kirchhoff's current law equation, I'm also going to keep track of this neutral current here, INN. So before we move on from this point, I want you guys to notice something. If our load is Y connected, the impedance of our Y connected load is just in series with the impedance of our transmission line. So this phase current, I believe I used blue for this. Sorry, what was that? So this phase current IAN is literally the exact same thing as IAA. This phase current IBN is the same thing as IBB. And this phase current ICN is the same thing as our line current ICC. So we are trying to figure out a relationship between these phase currents. So I'm going to say that the current that's entering this large node over here, all of the currents that are entering that node have to be equal to 0 because that's just Kirchhoff's current law, right? So applying Kirchhoff's current law, we could say that the current IAA plus the current IBB plus the current ICC plus the current INN is equal to 0. So we are about to apply effectively Ohm's law to this network. And so I'm going to do something here really quickly. And this is purely for mathematical purposes. I am going to consider my source side neutral to be my reference. Okay. Now, in a physical system, it's likely that the source side neutral would actually be tied to ground, but it is not in any way, shape, or form required. Okay. So for our intents and purposes here, we are doing this purely to make the math a little less overwhelming. This may not physically be the case in our system, okay? But it's just giving us a reference that we're going to refer everything to. Okay. All right, so I can use Ohm's law. And really, it's kind of Kirchhoff's voltage law here in order to express all of my line currents. So let me explain explicitly what I mean here, okay? I'm going to call this voltage, I'm going to do it in purple here, V capital N lowercase n. So that's just the voltage drop across my neutral conductor of my transmission line network, okay? Positive polarity is on the capital N side, negative polarity is on the lowercase n side. So if I were to write a Kirchhoff's voltage law expression around this path, what I would find is that the voltage drop across the impedance ZWA in series with ZYA is nothing more than the voltage VAN, my source voltage, minus that voltage drop across my neutral conductor. So I can call that current IAA VAN minus VNN. That's my voltage drop. Now I'm going to divide by my impedance. So this is going to look like ZWA plus ZYA. Let me scroll back up here. I could write a Kirchhoff's voltage law loop around the B phase and get a similar result, and the C phase and get a similar result. Okay. So that's going to give me VBN minus VNN over ZWB plus ZYB, and then I'll have VCN minus VNN divided by ZWC, plus ZYC. And lastly, I will have V capital N lowercase n divided by the n. Equal to 0. So let's put a constraint on this system. Okay. So for a balanced network, this equation will reduce to, so I'm going to move that V capital N lowercase n over to the other side of the equal sign. So I'm going to have V capital N lowercase n over Zn will be equal to VAN minus VNN over ZW plus ZY. So here I'm assuming that all of my transmission line impedances are equal in value, so I'm just calling them all ZY, or excuse me, ZW. All of my load impedances are equal, so I'm just calling them all ZY. And I'm going to keep on trucking with this so that we'll get VBN minus VNN over ZW plus that same ZY plus VCN minus VNN divided by ZW plus ZY. And since I have a common denominator on the right-hand side, I could actually just lump all of those terms together. So what I'm going to do is I'm going to keep all of my phase voltage terms on the right-hand side of the equal sign, and I'm going to move all of that voltage drop across the neutral conductor terms over to the left-hand side of the equal sign. And so what that's going to give me is this relationship. So I'm going to have VNN times 1 over Zn plus 3 over ZW plus ZY is equal to VAN plus VBN plus VCN divided by ZW plus ZY. Yes.
When we set the constraint for it to be equal, I want to go back, I feel like I was writing.
Sure.
When they change how
So when our network is balanced, that means that all of our transmission line impedances are the same thing. So everywhere that I had ZWA, ZWB, or ZWC, I just replaced it with ZW because they're all the same thing. Anywhere I had ZYA, ZYB, and ZYC, I just replaced that with ZY because those are also all the same. Okay. Are we good? No?
Yeah.
Okay, perfectly reasonable question. All right, so if my voltage source is balanced, what does VAN plus VBN plus VCN equal to? Rock? You made me do this on Tuesday. 0. Yeah. So just to be really clear here, we have VAN plus VBN plus VCN. Because our voltage source is balanced, this looks like VAN times 1 angle 0 degrees plus VAN times 1 angle negative 120 degrees plus VAN times 1 angle negative 240 degrees, because we know that our magnitudes have to be the same and it's only the phase angle that's changing. So that's going to look like VAN times 1 angle 0 plus 1 angle negative 120 plus 1 angle negative 240 degrees, or VAN times 0. You can throw that into your calculator and prove that adding those 3 equal magnitude 120 degrees of phase separation signals together will literally just give you 0 all day, every day. So coming back up here then, that means the right-hand side of this equation is just equal to 0 because we have 0 divided by some combination of impedances, right? So if the right-hand side of this equation is 0, what does that imply about what's going on the left-hand side? Is it possible for 1 over Zn plus 3 over Zw plus Zy to be equal to 0? No, if those are real impedances, we are going to have some number there. So I have a voltage times some number is equal to 0. What does that mean? That the voltage literally has to be 0. So the voltage drop across my neutral conductor in a balanced system is 0. Oh, yes. So we can say VNN is equal to 0. And using this, let's see what's going on with the current through the neutral conductor. So that's going to be negative V capital N lowercase n divided by Zn. And this obviously has to be 0 as well. So in a balanced three-phase system, there is no voltage drop across the neutral conductor, and there is no current flowing through the neutral conductor, which means physically, it's doing nothing. It doesn't even need to be there. But even if it isn't there, we can actually treat it like it's a short circuit because we know the potential difference between those two nodes is always going to be 0, regardless of whatever impedance it has. That is going to be a key part of our analysis of these systems to make things easier. Even if it isn't even physically there, it seems like it's a short circuit. We'll come back to that in a couple of moments. So now let's continue on here and let's look at what's going on with our line currents, okay? So our line current IAA is from earlier, VAN minus VNN divided by ZWA plus ZYA. Well, in a balanced system, this simply becomes VAN over ZW plus ZY. Our B phase line current formally is VBN minus VNN over ZWB plus ZYB. Well, this is just VBN over ZW plus ZY, but we can take this a little bit further, okay? So recognizing that VBN is the same thing as VAN, but with a 120-degree phase shift, this looks like VAN times 1 angle negative 120 degrees over ZW plus ZY, or simply our line current IAA multiplied by a factor of 1 angle negative 120 degrees. Meaning that if we were able to calculate the current flowing through the A phase of our system, we don't actually have to do any work to get the current flowing through the B phase of our system. We could simply shift it by 120 degrees, and it's the exact same thing as if we had done all of the analysis. Shouldn't be any stretch of the imagination to figure out what's going to go on with our C phase. So that's going to look like VCN minus VNN over ZWC plus ZYC, which will be VCN over ZW plus ZY, or VAN times 1 angle negative 240 degrees over ZW plus ZY, or simply IAA times 1 angle negative 240 degrees. So the C phase is just exactly what's going on in the A phase, except we shift it by 240 degrees, okay? Now we can mathematically do more of this stuff, but let's just talk our way through some things here. So we know that in a balanced three-phase system, all of our phase voltages at the source are equal in magnitude, separated in phase by exactly 120 degrees. Now we know that all of our line currents are equal in magnitude, separated in phase by exactly 120 degrees. Let's scroll up here. Let's look at this diagram, right? So I have already drawn the phase currents through my load, okay? The phase currents through my load are equal to my line currents because this is a Y-connected system. So that means the phase currents through my load are equal in magnitude, separated in phase by exactly 120 degrees. If I draw the phase currents through my source, how are these related to my line currents? Equal but opposite direction, right? So they're just the negative of the line currents. So they are all still going to be equal in magnitude and 120 degrees out of phase with each other. What about my, trying to remember what color I did these in. I think it was just black.
Solve balance, we solve A, so solve Y, and have it. Like, do you just need to solve one button?
Yeah, that's the whole point. That's what I'm trying to illustrate to you guys, but we're just kind of proving it step by step that it's going to work that way for literally everything, okay? But fantastic intuition there. So I'm drawing these line voltages, excuse me, phase voltages at my load here. Why are they all going to be equal in magnitude, but separated in phase by 120 degrees? Because the current flowing through them is equal in magnitude and separated in phase by 120 degrees, and all of the impedances are identical. As it will turn out, the exact same thing will happen for my line voltages on the load and the current. I know, it's mind-blowing, right? So we did all of this weird hippie math effectively to show that everything that's going on in the A phase is exactly the same thing as going on in the B phase, is exactly the same thing as going on in the C phase, except that there's 120 degrees of phase separation.
So then. Just break each section's like its own little thing and then solve.
You're 100% correct. That little section that you mentioned is what's called a single phase equivalent circuit for this three-phase system, which is absolutely what I'm going to introduce next, okay? So our single phase equivalent circuits. It's wonderful from my side of things for what it's worth, okay? So the reason why we're able to draw this single phase equivalent circuit is because we know that in a balanced system, all of our voltages and currents, line voltages, line currents, phase voltages, and phase currents will all have equal magnitudes, and they will all be 120 degrees out of phase with each other. Additionally, we know that our neutral conductor, regardless of what its actual impedance is, will always have a 0-volt drop over it, meaning that we can treat it like a short circuit. So we can subdivide our balanced three-phase YY network into three independent single phase equivalent circuits. Okay. So for the A phase, our single phase equivalent circuit is going to look something like this. So here's my lowercase a terminal for my phase voltage. Here's the voltage VAN. Here's my lowercase n terminal. Over here on the right-hand side, I'm going to put my load impedance. It's connected between my uppercase a terminal and my uppercase n terminal. Connecting lowercase a to uppercase a is my transmission line impedance, ZW. And then connecting lowercase n to uppercase n is simply a short circuit because we know that there's no voltage drop across the neutral conductor. We could do the same thing over here for the B phase. It's entirely unnecessary. But if we were given information on the B phase as opposed to the A phase, I guess it could have its uses. And lastly, over here, we'll do our C phase. Like so. So these are our single phase equivalent circuits. Now, let's talk about what quantities that we can get directly from this single phase equivalent circuit. Because there are some that we can get directly, and there are some that we're going to have to go back and get using more conventional circuit analysis techniques, right? So let me ask you guys a simple question. Do these circuits look easy to analyze? I think so, because it's just a voltage source and two impedances, right? So we took our giant, ugly three-phase circuit and broke it down into three smaller, very, very easy to analyze circuits. So I believe fundamentally that we should be able to determine our line currents, right? IAA, IBB, and ICC very easily. Just for the sake of argument, how might we go about doing that? Let's just worry about the A phase here. So VAN divided by ZW, but that's not going to be it. Plus ZY, absolutely right, because the whole voltage drop of VAN occurs over those two impedances connected in series. So once we know IAA, we know IBB and ICC just by shifting IAA by 120 and 240 degrees respectively. What about this phase current IAN, or these equivalent phase currents IBN? So is this one going to be negative IAA or is it not? It- in the same direction, so it's going to be the exact same thing. So our phase current through the load is literally just going to be the exact same thing. What about our phase currents through our source? This is the one that's negative. So let's put it over here. That one's just negative IAA. All right. So what about the phase voltage across our load? We're solving for VAN. It's just Ohm's law. We have current, we have impedance. I times Z. Yep. So IAN times ZY. So those are all of the different things that we can solve for using the single phase equivalent circuit. Okay. We can solve for our phase voltages in our YY system. It doesn't matter if it's on the source side or the load side. We can solve for our phase currents in our system. Doesn't matter if it's the source side or the load side. And we can also solve for our line currents. We cannot directly solve for our line voltages because these are three independent circuits. And our line voltages, by definition, are measured between transmission line terminals. So we'd be looking for the voltage between terminal A and terminal B. There is no terminal B in the A phase equivalent circuit. So that can't be done. However, if we look up here, we can figure out those relationships pretty easily. We're going to wind up using these significantly. So if, for whatever reason, we needed this voltage VAB, or this voltage V capital A capital B, so the source side line voltages or the load side line voltages. Let's come down here and let's sort this stuff out. And I think we actually wound up doing this on Tuesday as well. But we could see from the inspection of our three-phase circuit, VAB is nothing more than VAN minus VBN, which comes out to be VAN times root 3 angle 30 degrees. Similarly, VAB on the load side is literally nothing more than capital VAN minus capital VBN, which comes out to be capital VAN angle, or excuse me, root 3 angle 30 degrees. So now we have a mathematical expression for literally every possible quantity that I could ask you about in a YY system. So I'm going to open up our in-class assignment and we're going to work some examples putting this stuff into use. Casey, did you have a question? Mm-hmm. 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 Where do you see IAN minus IAA? So that is the phase current through our source. So the I capital A capital N is the phase current through our load, and the I lowercase a lowercase n is the phase current through our source. VAB, or excuse me, V lowercase a lowercase b is the line voltages across our source. The uppercase A uppercase B is the line voltages across our load. All right, so that is correct, square root of 3. Let me write that 3 slightly less shittily. There you go, Stuart. Let me make sure that angle sign looks like an angle sign and not a letter C. So let me explain exactly where that's coming from, right? So we're doing Kirchhoff's voltage law around this path. So we would have negative VAB, because we see the negative polarity terminal first when we go up. Then we see the positive polarity terminal of our voltage VAN. And then we see the negative polarity terminal of our voltage VBN is equal to 0. And so we could move that VAB to the other side of the equal sign, giving us this relationship. All right, we'll close that data sheet out. Let's open up this in-class assignment. So in our first problem, we are told that we have a positive phase sequence balanced 3-phase Y-connected source with a phase voltage of 120 volts RMS in magnitude. And it supplies power to a balanced Y-connected load with a per phase impedance of ZY is equal to 40 plus J10. And we're simply asked to determine our line currents if the angle of the voltage VAN is equal to 0 degrees. So I'm going to draw a picture representative of this circuit. Was there a transmission line impedance mentioned at all? Nope. So we're going to assume it's 0 because we were not told otherwise. So this is what our circuit would look like as a 3-phase system. Let's parse through the information that we were told. So we know that the magnitude of our A-phase voltage was 120, and the angle was 0 degrees. So I'm just putting those two pieces of information together to call voltage VAN 120 angle 0 degrees. We were also told that our load impedance is 40 plus J10 ohms, and that's it. So from this, let's construct our single phase equivalent circuit. So I have a 120 angle 0 degrees volt RMS source. And then I have my ZY is equal to 40 plus J10 ohm impedance. And we are specifically asked to find our line currents, right? So my line current is the current that's flowing from transmission line terminal lowercase a to transmission line terminal uppercase a. So how would I find IAA? Yeah, exactly right. So it's just going to be 120 angle 0 degrees volts RMS divided by 40 plus J10 ohms. Toss that into my calculator really quickly. I got 2.910 with an angle of negative 14.036 degrees. Amps RMS. Sorry, I ran out of room there. I transposed the answers on the paper. It should be 036. I'll need to fix that. Yeah, it's just me fat fingering and then copying and pasting. Sorry about that. So how are we going to get IBB? So the magnitude is going to be exactly the same, 2.910. We subtract 120 degrees from the phase angle. So negative 134.036 degrees amps RMS. No circuit analysis whatsoever needed. Literally, just take the answer that we got from the previous step, subtract 120 degrees from the phase angle, go on about our day. ICC is going to be the same thing, 2.910, and now we're going to subtract 120 degrees for what we had on the B phase, which would be negative 254.036 degrees amps RMS. One problem down, 2 to go. Was this difficult? I hope the answer is no. Brianna, how may I help you? A RMS. These are all currents, so they're all measured in amps RMS. All right. Are we good to move on to the next problem? Okay, that one was rather simple. So this one is a little bit more difficult. So we have a positive phase sequence, balanced 3-phase Y connected source with a phase voltage of stuff, supplies power to 2 balanced Y connected loads in parallel. The loads have impedance of ZY1 is equal to 15 plus J8 and ZY2 is equal to 12 minus J5. The transmission line connecting the source to the loads has an impedance of 0.3 plus J0.05. And we are asked to determine the phase currents in each of the parallel loads. So this is something that's kind of new because instead of having a single load, we now have 2 loads that are connected in parallel to each other. So let's draw a picture that represents what that's going to look like. Okay. So I'm going to start with my source. I was told it was Y connected. So here's VAN. VBN. VCN, lowercase a, b, and c. We have a transmission line impedance to worry about this time, so I'm going to put in my ZWs. And now I need to figure out what's going on with my loads. So I'm going to start just by putting one of the loads in. Okay. And you'll see why I'm drawing it oddly in a second. So this should say ZY1, but it's hard to read. So here's my first load. And notice that each phase of my load is connected between the appropriate transmission line terminal and the neutral terminal, because that's how a Y-connected load is always connected. So if I were to put a second load in parallel with this, the A phase of that load has to be between the A terminal and the neutral terminal. The B phase has to be between the B terminal and the neutral terminal, and so on and so forth. So it's literally just putting the two phases, or the two portions on the A phase in parallel with each other. Putting the two portions on the B phase in parallel with each other, and putting the two portions on the C phase in parallel with each other. Anything confusing about that? It's just connecting them in parallel. So let's say that you're trying to power a manufacturing plant and there are two induction motors. That realistically, and likely haven't thought about this, if I were to plug, let's say, a microwave into this outlet down here and a toaster oven into the receptacle below it, that is the single phase equivalent of what we've done here. Or because all of these circuits along this wall are probably literally wired in parallel to the same breaker, if I plug something into this receptacle and then one into one of the receptacles down there, as long as it's a 120 thing, it's the exact same thing. There are, our voltage source would be in our breaker panel. Our transmission lines would be the wires that are connecting our breaker panel to these receptacles, where these receptacles are pretty much just the terminals that we are connecting our loads to. It's just that exact same thing, but with a three-phase system. All right, so how are we going to, yes?
Well, that explanation was good. What if we have, how does the load change when you have like different frequencies separate? Like how does that affect the?
So when you have different, are you talking about using a variable frequency drive? Okay, so the variable frequency drive is the load. It's an interface between, yeah. So your three-phase would go into each VFD, and then that VFD job would be to correct the to set the frequency for that specific motor.
So you can almost look at that as like one of the.
Yeah. So realistically, that kind of thing you would have, so here's the A phase transmission line. So you would have the A phase of the VFD connected to the A phase of the motor, and then here's the neutral. So it would see those things in series effectively. But you could lump it all together as a single impedance because that's how impedances work. Yeah. Ooh. Yeah. Yep. Okay, so how do we draw our single phase equivalent circuit? Yeah. So between lowercase a and lowercase n, we have our voltage source. Between lowercase a and uppercase a, we have our transmission line impedance. Between uppercase a and uppercase n, we have an impedance ZY1 as well as an impedance ZY2. And between lowercase n and uppercase n, we have a short circuit. So I didn't take the time to write things down, so let's do that really quickly. So we're told that VAN was 230 angle 0 degrees. ZW is 0.3 plus J 0.05. ZY1 is 15 plus J8. ZY2 is 12 minus J5. We were asked to find the phase currents in each of the parallel loads. So that means that we're looking for this current, which I'm going to call IAN1 flowing through ZY1, and this current IAN2 flowing through ZY2. So if I wanted to find both of those currents, how could I do it? I can think of like 3 different ways off the top of my head, some of them easier than others. So you're saying, Trilin, if I'm understanding you correctly, that if we were able to find the phase voltage across our loads, because our loads are in parallel, they're identical, we could divide that phase voltage by the impedance of each load, and that would give us our phase currents. I agree with that 100%. No, that's just. So how would we find that VAN?
Same way last time I said we would do a parallel circuit now.
Well, you could go current route, which is the equivalent plus zero.
You guys remember voltage division at all?
Do this for, so ZY1 plus ZY2 over ZY1 times one.
That's the end.
And then get your Z total, your ZY total for the first one, and then you can just do our equation. VAN over ZW, or ZY, sorry. ZY plus ZW.
So to me, the voltage VAN could be easily determined by using voltage division, where I would have my known voltage, which is the source voltage, multiplied by the impedance I'm trying to find the voltage drop over, which in this case is ZY1 in parallel with ZY2. So I'm going to write that as ZY1 times ZY2 over ZY1 plus ZY2 divided by the total impedance seen by the voltage source, which is just ZW plus that parallel combination of impedances. I'm not saying that there is anything remotely wrong with finding the equivalent impedance of the whole thing, finding the current, leaving the positive polarity terminal of the source, and then doing effectively KVL to find VAN. I'm just lazy, and if I can do it in one step, I'm going to. And that's what that would look like.
Yeah, my brain doesn't like, goes with this. I don't know a lot of that.
Yeah, so just, I'm not doubting that you understand it, but just to be clear, effectively what we have is this circuit, and we're just trying to find the voltage drop across that one impedance, which to me, anytime I have a voltage source in series with impedances, screams use voltage division. Again, purely because I'm lazy and I want to get there without having to think too much. Nothing, like I said, remotely incorrect about the methods that you guys suggested, just a little less inefficient. So let's see here. So this is 230 angle 0. ZY1 was 15 plus J8. 12 minus J5. 15 plus 12 is 27. Plus J3 all over 0.3 plus J 0.05 plus, and I'm going to be lazy here and just write numerator because it's literally exactly what we have in the numerator. And I'm going to throw this into my calculator real quick. So 15 plus 8i times 12 minus 5i over 27 plus 3i. Oops, 12 minus 8 when my calculator has input lag. I got 221.837 with an angle of negative 0.371 degrees volts RMS. And from here, IAN1 is just VAN over ZY1. So that would be that answer divided by 15 plus 8i. I get to be 13.049 with an angle of negative 28.444. Excuse me, this should be amps RMS. And IAN2 would just be that voltage VAN over ZY2. So 12 minus 5. 17.064. Angle positive 22.249. Sorry. Let me just double check here. Seems legit. And obviously, to get the B phase, we would just subtract 120 degrees. To get the C phase, we would subtract 240 degrees. So that one was a little bit harder. But I don't think it was wildly difficult by any stretch of the imagination because the single phase equivalent circuit makes these pretty straightforward to look at as long as we're looking for something that's given us. So before we move on to problem 3, anybody have any questions about what we did here. It's up to you. The in-class assignments are not graded for completeness or correctness. They are graded as participation. So since you were here working on it, whatever you write down is good to me, Sam.
Oh, this question we given the whole
PW, we did.
Oh, I want, yeah.
All right, anything else? All right, so let's see how much of a jerk I was on problem 3. So for problem 3, we once again have a 3-phase YY system. We are given line current and line impedance, and we're given the line voltages at the source, and we are asked to determine the load impedance per phase. So let me write some things out here. So we have our YY system. Here's VAN, VBN, VCN. I'm going to draw this in green because that's what I've been doing for line voltages. So we were given this line voltage VAB. We were not given the voltage of our source. Okay. Then we have a transmission line with an impedance of 1.2 plus J 1.8. So let's call that ZW here in the middle. And we have a Y-connected load whose impedance we are trying to find. And we are also given our line current IAA. So let's write some things down here. So the voltage VAB was 440 angle 70 degrees volts RMS. Our line current IAA is 16.78 angle 20.98 degrees amps RMS. And the impedance of our transmission line is 1.2 plus J 1.8 ohms. So we are still going to use our single phase equivalent circuit here, but now it's going to take a little bit of effort in order for us to construct it because we weren't given all of the information that we have been. Okay. So our single phase equivalent circuit should look something like this. Here's our voltage VAN. Here's our transmission line impedance ZW. Here is our load impedance ZY that we're trying to find. We are given our transmission line impedance IAN. So let's think about some things here really quickly, okay? Ultimate goal of this particular problem is for us to determine the impedance ZY. Impedance, hopefully you guys remember this, is fundamentally just the ratio of a voltage drop across some network divided by the current flowing through that network, right? So ZY will be whatever this voltage VAN is, divided by whatever this current IAN is. Are we all okay with that? That's just Ohm's law, right? So I'm going to write that down over here. ZY is just VAN over IAN. Okay. So how are we going to solve for either VAN or IAN? Well, I think one of them is very easy. Casey, you want to help me out with the current? Nope, okay. That's all right, Nick. Yeah, absolutely. So for our single phase equivalent circuit, the impedance ZY looks to be in series with the impedance ZW. Since we were given the IAA, that's just IAN, right? So IAN is equal to IAA is 16.78 angle 20.98 degrees amps RMS. Okay. So we've got one of our two pieces of missing information taken care of already. So we're off to a good start. Now, I believe that we could solve for that voltage VAN using voltage division like we did. Actually, we won't be able to do that because we would need to know what the impedance ZY is first. So we're going to have to think of a different way to do it. So this kind of goes back to what you guys were suggesting earlier. That voltage VAN would be equal to our source voltage VAN minus the voltage drop across our transmission line, which would be that current IAA times the impedance ZW. Now, one problem with that is we don't have that. We have something else. Yeah, so how do we take our VAB and extrapolate? No. We have VAB. We don't have VBN. Yeah, so let's pop back over here to these relationships that we talked about. So this is, we were given one of the pieces of information that we can't get for our single phase equivalent circuit, but we have absolutely right. So VAN is just going to be VAB divided by √3 angle 30 degrees. So this would be 440 angle 70 degrees volts RMS divided by √3 angle 30 degrees minus 16.78 angle 20.98 amps RMS. I'm running out of room here. So I'm multiplying that. I'm just going to write in ZW here because I ran out of room, and we'll put that in the calculator real quick. So 440 angle 70 over √3 angle 30 minus 16.78 angle 20.98. ZW was 1.2 plus 1.8 I. And I got 226.226 with an angle of 34.421 volts RMS. And now I'm simply going to divide that answer by the 16.78 angle 20.98. And I wind up getting 13.482 with an angle of 13.441 degrees ohms, which matches what we got up here. All right. So we've worked all three in-class assignment problems. So we're wrapped up about 25 minutes early. So what we're going to do on Tuesday's class meeting is we are going to figure out how to make delta connected loads look like Y connected loads, and how to make delta connected sources look like Y connected sources, so that we can apply this single phase equivalent circuit method to literally any type of three-phase circuit that we could possibly be given. Because I fundamentally believe this analysis isn't that bad. So this is the easiest way to go about it, okay? So we're gonna do some theory at the beginning of the class, figuring out how to do those transformations. They're called delta Y transformations. We're gonna learn it for sources and impedances. And then we're gonna apply that and all that kind of good stuff. I'm gonna put a homework assignment up that'll be due a week from today. It might have some problems that you won't be able to do until after class on Thursday. But I'll put like the first couple you should be able to do today, and then the rest you should definitely be able to do after Thursday's class meeting. So hopefully giving you guys plenty of time to get that taken care of. All right, thank you guys.